Welcome to iqpod.io, where Ava and David, your expert AI hosts, bring you the latest developments in the neural rendering and 3D reconstruction field. They discuss significant papers and their implications.
Today, we're diving into two exciting papers in the field of visual SLAM, or simultaneous localization and mapping. Both papers, Gaussian-SLAM, photorealistic dense SLAM with Gaussian splatting, and Gaussian splatting SLAM, introduce novel approaches to scene representation using 3D Gaussians. This is a significant departure from traditional methods like point clouds, circles, or voxel grids.
That's right, David. The use of 3D Gaussians seems to be the common thread here. Can you explain why this is such a big deal?
Absolutely. You see, the way a SLAM system represents the environment is crucial. It impacts everything from memory efficiency and computational complexity to the level of detail that can be captured. 3D Gaussians offer a balance between these factors. They can provide a continuous, smooth representation of geometry while still being efficient to work with.
Interesting. So what specific problems are these papers trying to address with this new representation?
Well, Gaussian SLAM is focused on achieving photorealistic reconstruction and rendering in real-world scenarios. They want to push the boundaries of visual fidelity while still maintaining real-time performance. On the other hand, Gaussian Splatting SLAM seems to be more concerned with the overall efficiency and scalability of the SLAM pipeline.
I see. And how do these objectives differ from previous work in the field?
That's a great question. Traditionally, SLAM systems have often had to make trade-offs. Methods that provide detailed, dense reconstructions like those based on circles or high-resolution voxel grids can be computationally intensive. Sparser methods, like feature-based approaches, are more efficient but don't provide the same level of detail.
So these papers are trying to get the best of both worlds, in a sense.
Exactly. They're leveraging the unique properties of 3D Gaussians to strike a balance. Gaussian SLAM, in particular, draws a lot of inspiration from the work on neural radiance fields, or NeRF, which has achieved impressive results in photorealistic rendering but has been limited in terms of real-time performance.
That's a fascinating connection. Can you elaborate on how Gaussian SLAM builds upon the ideas from NeRF?
Sure. NeRF uses a neural network to represent a scene as a continuous function that maps 3D coordinates to color and density. This allows for high-quality rendering, but requires a time-consuming optimization process. Gaussian SLAM takes a similar continuous representation approach with 3D Gaussians, but introduces several innovations to make it more suitable for real-time SLAM.
Such as?
Well, they introduce an efficient method for initializing and updating the Gaussians based on incoming depth data. They also propose a novel tracking approach that allows for direct alignment between the Gaussian map and new frames. These contributions allow Gaussian SLAM to achieve NeRF-like quality while operating in real time.
That's impressive. And what about Gaussian Splatting SLAM? How does it differentiate itself from prior work?
Gaussian Splatting SLAM puts a strong emphasis on scalability. They introduce a submapping approach where the global map is broken down into smaller, more manageable chunks. This allows them to bound the computational complexity and memory usage, even as the size of the environment grows.
That sounds like a significant advantage for large-scale applications.
Definitely. They also introduce some interesting ideas around map optimization and keyframe selection to further improve efficiency. In terms of novelty, both papers are really pushing the boundaries of what's possible with dense, visually appealing SLAM in real-world scenarios.
It's clear that these papers are tackling some fundamental challenges in the field. I'm curious to see how their proposed methods perform in practice.
Absolutely. Both papers include extensive evaluations on benchmark datasets and real-world sequences. They compare against state-of-the-art methods in terms of tracking accuracy, reconstruction quality, and runtime performance. The results are quite promising, with significant improvements shown in photorealistic rendering and efficiency.
That's exciting. It seems like these 3D Gaussian-based approaches could really change the landscape of what's possible with real-time, visually detailed SLAM.
I agree. It's a significant step forward. Of course, there are still open challenges and room for improvement. Handling dynamic scenes, for example, remains a difficult problem, but these papers lay a strong foundation and open up a lot of interesting avenues for future research.
Definitely. I think this is a space we'll want to keep a close eye on. The potential applications from AR and VR to robotics and autonomous vehicles are vast. Let's dive a bit deeper into the specifics of each paper. David, can you walk us through the key methodological contributions of Gaussian-SLAM?
Sure thing, Ava. Gaussian-SLAM introduces several novel components in their pipeline. Firstly, they propose a direct tracking approach that allows for the camera pose to be optimized directly against the Gaussian map. This is in contrast to many existing methods that rely on indirect feature matching. They derive an analytical Jacobian that enables this direct optimization, which is a significant technical contribution.
That's interesting. And what about their mapping approach?
For mapping, they introduce a novel method for initializing and updating the Gaussians based on incoming depth data. They use a combination of spatial hashing and a weighted average scheme to efficiently allocate and merge Gaussians. They also propose an adaptive scheme for adjusting the resolution of the Gaussians based on the depth uncertainty.
How does this compare to the approach taken in Gaussian Splatting SLAM?
Gaussian Splatting SLAM also uses 3D Gaussians for mapping, but they take a slightly different approach. They introduce a submapping scheme where the global map is divided into smaller, more manageable chunks. Within each submap, they use a combination of uniform and color-based sampling to initialize the Gaussians. They also introduce a novel visibility-based culling scheme to prune redundant Gaussians.
So both papers are using 3D Gaussians, but they differ in how they manage and update these Gaussians over time.
Exactly. Gaussian-SLAM puts more emphasis on the direct tracking and adaptive resolution aspects, while Gaussian Splatting SLAM focuses on efficient map management and scalability.
That makes sense. Now let's talk about the experimental setup. How did these papers evaluate their proposed methods?
Both papers conduct extensive evaluations on a range of benchmark datasets and real-world sequences. Gaussian-SLAM evaluates on the TEAM RGBD and ICL and UM datasets, which are standard benchmarks for indoor SLAM. They compare against several state-of-the-art methods, including both sparse and dense approaches.
And what about Gaussian Splatting SLAM?
Gaussian Splatting SLAM also uses the TEAM RGBD dataset, but they additionally evaluate on the more challenging ScanNet and ScanNet++ datasets. These datasets contain larger, more complex scenes, which really test the scalability of their approach.
Interesting. And what were the key findings from these experiments?
Both papers show significant improvements over existing methods in terms of tracking accuracy, reconstruction quality, and runtime performance. Gaussian-SLAM demonstrates superior performance in photorealistic rendering, with their direct tracking approach enabling highly accurate pose estimation. Gaussian Splatting SLAM shows impressive results on the larger ScanNet datasets, validating the effectiveness of their submapping and culling strategies.
Were there any weaknesses or limitations identified in these experiments?
One area that both papers acknowledge as a challenge is handling highly dynamic scenes. While they demonstrate robustness to some level of dynamic content, scenarios with significant motion or occlusion can still cause issues. Gaussian-SLAM also notes that their current implementation relies on a GPU for real-time performance, which could be a limitation for certain applications.
That's a good point. I noticed both papers include quite detailed ablation studies. Can you summarize the key findings from these?
Absolutely. Gaussian-SLAM performs ablations on several of their key contributions, including the direct tracking, adaptive resolution, and depth-based initialization. They show that each of these components contributes significantly to the overall performance, with the direct tracking being particularly crucial. Gaussian Splatting SLAM ablates their submapping and visibility-based culling schemes, demonstrating their importance for scalability and efficiency.
It's clear that a lot of thought and rigorous experimentation went into both of these papers.
Definitely. Both papers also include extensive appendices with additional details on their implementations, parameter settings, and experimental setups. This level of transparency and reproducibility is really valuable for the research community.
Absolutely. So, to summarize, both Gaussian-SLAM and Gaussian Splatting SLAM introduce novel approaches to dense SLAM using 3D Gaussians. While they share this common representation, they differ in their specific contributions and emphases. Gaussian-SLAM pushes the boundaries of photorealistic reconstruction and direct tracking, while Gaussian Splatting SLAM focuses on scalability and efficient map management. Both papers demonstrate significant advances over the state of the art through comprehensive experiments and ablations.
That's a great summary, Ava. These papers really showcase the potential of 3D Gaussians as a powerful representation for SLAM. The improved performance and visually compelling results open up exciting possibilities for a wide range of applications. At the same time, the authors are upfront about the remaining challenges and areas for future work, such as handling highly dynamic scenes and further optimizing computational efficiency.
It will be fascinating to see how this line of research evolves and what new innovations build upon the foundations laid by these papers.
Absolutely. Gaussian-SLAM and Gaussian Splatting SLAM represent significant milestones in the quest for high-quality, real-time dense SLAM. They set a new bar for what's possible and provide a springboard for further advancements. It's an exciting time in the field, and we look forward to seeing what breakthroughs come next.
As we wrap up, let's credit the authors and their institutions. Gaussian SLAM, Photorealistic Dense SLAM with Gaussian Splatting, was authored by Vladimir Uge, Yue Li, Theo Gevers, and Martin R. Oswald, all from the University of Amsterdam.
And for Gaussian Splatting SLAM, the paper comes from a collaborative effort by Hidenobu Matsuki, Riku Murai, Paul H. J. Kelly, and Andrew J. Davison at the Imperial College London, specifically from the Dyson Robotics Laboratory and the Software Performance Optimization Group.
Just a reminder, this discussion is generated by an AI language model, so some details might not be completely accurate. For any further questions or feedback, feel free to reach out to us at questions@iqpod.io.